Let's look next at angular momentum in section 12:11. Angular momentum is the vector moment of linear momentum. So we can start off with that definition. The letter symbol for angular momentum is L. Let's consider an object moving in a plane about an axis. So we can draw this in 3 dimensions this way. So we have the z-axis, x, and y. Suppose that there is a particle in this object at a certain point here. This particle is at a distance r from the axis, and there is an angle between that particle and the momentum vector p given by the mass of the particle multiplied by the velocity v, which is at a tangent to the location of that particle. Suppose the angle between the vector r and the vector p is given by phi. Then we can say that the momentum, or in this case the angular momentum of this object, the angular momentum would be given again by the vector r, and then let's find the vector b. Let's put it somewhere here like that. Let me redraw that to make sure that it works out the way we want. Let's redraw this section here so that it works out the way we want it. So this angle is phi. So I'll put the momentum vector on this here and put the angle phi. So this is p and that is r. So the angular momentum vector is given by r cross p, and it's a vector that points perpendicular to the plane of r and p. So this section here is our plane of motion. It's the same as what we have here. So this is plane of motion. So the angular momentum vector L is defined quantitatively as L equals r cross p, which can be written as r cross m times v. So we can write it this way also. And angular momentum being a vector means that we can, the unit of angular momentum, so let's just do the unit, would be kilograms meters squared per second squared. Meter squared per second, not per second squared, sorry. Kilograms meters squared per second. So let's continue with angular momentum. We also found that we could rewrite Newton's law. So we know from previous chapters that we can write Newton's second law as F net equals d dt of mass times velocity, which is just momentum. So it's just d dt of the momentum, derivative of the momentum. We can do the same in rotational analog of Newton's second law. So since angular momentum, which is L, is the rotational analog of linear momentum, we can write the rotational analog of second law as follows. So we will take the second law and say that the rotational analog of the second law is the net torque is equal to the time rate of change of angular momentum L, like that. And then we'll replace angular momentum by the component r cross f. So we shall say r cross p, not r cross f, sorry, r cross p. So if you take the derivative of that, then we shall have d dt of the vector r cross p plus r, and then we'll do dp dt that way. So this then becomes v cross p that way plus r cross f net. So this gives us the net force, the net torque, not force, torque. Now we can say that since the vectors v and p are parallel to each other, the cross product of those two vectors is 0. So since v and p are parallel, so v is the velocity and p is momentum, their cross product is 0, so that we will see that the net torque is just equal to r crossed with f net. So which is basically our definition of torque. So F is just the net force, and so the net force multiplied by the lever arm is your net torque. Let's put the vector notation on this. So what this tells us then is that the net torque is just equal to the time rate of change of angular momentum. So time rate of change of angular momentum is equal to net torque. So this is the rotational analog of Newton's second law. Let's look at how this can be used. Suppose we have an object that has several vectors of angular momentum on it. We can see what happens. So what we've written down as the rotational analog of the second law, we found by looking at the angular momentum, or we found the angular momentum of a single particle. Suppose we have a rigid body composed of multiple particles, then we can find the net angular momentum as shown. So I can say that the formula above, so suppose we have a body made up of multiple particles with individual angular momenta, let's say L1, L2, and so on. We can write the net angular momentum L net to be equal to L1 plus L2 plus Ln. Of course, these are all vectors. And so L net is equal to the sum of all the angular momentum vectors, L subscript I, like that. And we can combine this with Newton's second law for rotational motion. So in this situation, we shall have the net torque, which we know is just d dt times the angular momentum. And this time, suppose we have multiple particles, then we can say that the net torque is the sum of all the individual torques, and this can be written as the sum of all the individual angular momenta, like that. And of course, this can be written as dl dt, like that. So this is just telling us that the rate of change of angular momentum is equal to the net torque on the system. So let's look at angular momentum and linear momentum and compare the two. We shall do that in a table. And so on this side, we have rotational kinetic energy, which is equal to half of the rotational inertia times angular velocity squared. And compare that to the kinetic energy of the center of mass of a rigid body. That will be half of the mass times the velocity of the center of mass squared. And then we shall have the angular momentum, which is equal to rotational inertia times angular velocity. That will be a comparable analog of the linear momentum, which is equal to the mass times the velocity of the center of mass. And then our net torque is equal to the time rate of change of angular momentum, and that can be written similarly as net force equals to the time rate of change of linear momentum. We will talk next about angular momentum and its conservation, and before I do that, I'll define angular momentum for you in a slightly different way. So let's rewrite angular momentum in a different way. So we said our angular momentum L is the vector moment of linear momentum, and we wrote it as R cross P that way, where the linear momentum P is equal to the mass times velocity. Suppose we have an object, and I'm referring to a rigid object or rigid body below. So we have this plane object like that, and we have a certain point in this object where there's a mass m at a certain distance r, and let's say that the velocity is v. Let me rewrite this. So velocity is something like that. So then we shall have something that looks like that. So we have r, again, this is the mass m, velocity is this way, so this is momentum p, which is equal to mv. Okay, so these are all vectors, as you can see. So if this object is rotating with a certain angular velocity omega about the axis, then what we have is we can write v to be equal to r times angular velocity omega, and then we will replace that in our formula. So our angular momentum L is equal to R times mv, or R cross mv, which can be written as R m, and v is R omega, so we can write it as m R squared omega that way. For a single particle, mr squared is recognized as the inertia I, so we can say that I is equal to mr squared for a single particle rotating about an axis where the particle is at a distance r from the axis. So we can rewrite angular momentum L to be equal to I times angular velocity, where angular velocity is a vector quantity, so you just put a vector notation on it. So this is a second way of writing angular momentum using the rotational inertia. So this is the rotational analog of linear momentum, where linear momentum was written as E equals m times v. Okay, so let's go on to the conservation of angular momentum next. We saw previously that in order to conserve linear momentum, we were able to do that if we showed that the net force on the object was equal to 0. So I'll remind you of that. So in our linear momentum conservation, the net force is equal to 0. So in Newton's second law, which we wrote as that F net equals the rate of change of the linear momentum, we will set that equal to 0, and that allowed us to do linear momentum conservation. We can do the same thing for angular momentum conservation. So we'll say that similarly, if the net torque on a system of objects is equal to 0, then the time rate of change of angular momentum can be written as equal to 0. And this will mean that angular momentum is conserved. So we can say that the net torque equal to 0 can be written as the change in angular momentum with respect to change in time. And if net torque is equal to 0, then we will say that the change in angular momentum with respect to time is equal to 0. Therefore, angular momentum is change in angular momentum is equal to 0, where the change in angular momentum is equal to the final angular momentum minus the initial angular momentum, and that we set equal to 0. So this means then that final angular momentum is equal to initial angular momentum. This is our angular momentum conservation principle. And if we want to write that using the rotational inertia, then we can say L final is I final omega final, and L initial is equal to I initial omega initial. Therefore, we can say that final inertia, final angular velocity is equal to initial inertia, initial angular velocity. Let's look at the example of two interacting disks. This is example 12.21 in the textbook. In this example, a disk is initially rotating at a certain angular velocity, and the second disk is dropped onto it. So the question is to find the final angular velocity of the combined system of the two disks. So we can recognize this as a system where there is an inelastic collision between two rotating disks, and we can use our conservation of angular momentum principle to do this calculation. So in this example, a 20 centimeter diameter disc. So in this example, a 20 centimeter diameter 2 kilogram solid disc is rotating at 200 RPMs. A 20 centimeter diameter 1 kilogram circular loop is dropped straight down onto the rotating disc. Friction causes the loop to accelerate until it is riding on the disc. What is the final angular velocity of the combined system? Let's first draw a diagram, and then we'll use angular momentum conservation to solve this problem. So initially, this is what we have. We have the rotating disc, and then above that is a second disc which is not rotating. So this is the loop. It's not really a disc, it's a loop. So M loop, and this is the disc. And the axis of rotation is this axis here. So they are rotating about a common axis. And then finally, after the disk is dropped, you have the system like that with the loop on it. So let's see if I can draw this better that way. So again, they are rotating about an axis through the center. So we have an initial angular momentum, which is the angular momentum of this disk. This is L initial. And then it will have a final angular momentum, L final. Let's get it closer. So L initial is equal to I initial, angular velocity initial. L final is equal to I final, angular velocity final. We want angular velocity final. That's what we are looking for. So our final angular velocity can be written as, or first of all, by angular momentum conservation, L initial is equal to L final. Therefore, final angular velocity will be given by I initial omega initial divided by L final. Sorry, not L final, I final. So I final is equal to I disk plus I loop, and I initial is just equal to I disk. So we know that the inertia of a disk about an axis through the center can be written as half m disk times r disk squared, and I of a loop, that is the inertia of a loop about an axis through the center, is just the mass of the loop times the radius of the loop squared. So we can replace these formulas into our final formula to get the final angular velocity, which is equal to half m for the disk times the radius of the disk squared. And by the way, the radius of the disk is the same as the radius of the loop, so we'll just replace that. This is the mass of the disk, radius of the disk squared, plus mass of the loop, radius of the loop squared. Note that r disk is equal to r loop. Okay, so they are the same. So plug everything in here and we can get our final angular velocity to be 100 rpms. Okay, so that's the example. So this is the end of chapter 12.